back to Stelzer Science. Today we are going to do the AP Physics Exam 2 review, both the multiple choice and the FRQ. As always, we'll split it up into two videos. So let's go ahead and dive into the multiple choice. Before we do that, however, I do want to go over just a few things before that. First, I think I want to go over is the equation sheet. So you are given this equation sheet on every single one of your exams. It's important to know what's on here. Because with Unit 2, there's a lot of things in Unit 2 that I think you forget that are on there. You don't have to memorize these equations. It starts off with Newton's second law right here. Newton's second law, F equals ma. It solves for the acceleration, so it does A equals F net over mass. So in order to find the acceleration of a system, it's the force divided by the mass. We have the big G force of gravity equation. Remember, when we're near the surface of the Earth, F of G just equals mass times gravity using Earth's acceleration. But if we're in space, we have to use this equation. We're also given down here on the other side what the constant of G actually is. So 6.67 times 10 to the negative 11th. You are given the force of friction equals mu times normal force. You are given that the spring force is negative kx, the spring constant, times the stretch or the compression. This is Hooke's law. So if you ever see Hooke's law in an AP physics question, that is what's referring to. And lastly, you are given that the centripetal acceleration is equal to the velocity, the tangential velocity squared, divided by the radius of the circular motion. We can extend this one, and if we look at F equals ma, centripetal force is just equal to mass times centripetal acceleration, or centripetal force is equal to mv squared over r. Pretty simple derivation there. Remember, centripetal force is not an applied force, it's a net force. The other thing I want to do before we start is just go over the basic type of question we see in this problem. And this unit. This unit's all about forces. And it's really always centered around Newton's second law, F equals ma. Or a lot of times I like to say F net equals mass times acceleration. This unit is all about just, can we use this equation? F net equals mass times acceleration. This equation kind of behaves differently in one of two situations. If our system is static, or if it is in constant velocity. So static, meaning not moving, or constant velocity. That means acceleration is equal to 0, which means F net is equal to 0. And how I like to do this problem, or problems like these, is I pick a direction as positive, and I say all the forces pointed in that direction equals all the forces pointed in the other direction. If there is acceleration, we're usually going to be wanting to find that acceleration, and this is where your equation sheet comes to play, because we can say that the acceleration of the system is equal to the net force, so find the net force, pick a direction as positive, all the forces in that direction minus all the forces in the other direction, divided by the mass of the system, equals the acceleration of the system. If you understand how to apply that, then this unit really just turns into, can you put forces correctly on a free body diagram? That's the hard part of this unit. Can you apply a force correctly? So with that out of the way, let's actually get into the review. And we're going to start off with the multiple choice. Let's keep it fall colors and do like an orange background with a red pen. And let's full screen this. No, I don't want that. Alright, let's start off with question 1 here. F equals ma. So we have a box of mass m slides up a ramp with an initial velocity v plus. So it's sliding up the ramp, not down the ramp. The kinetic friction force in the box has a magnitude of F. What is the following is the correct equation that could be used to determine the acceleration A of the box? So none of these equations are solving for A, but they all have A in them. It's asking which of these equations is just set up correctly. So first step, let's draw a free body diagram. And since it's on paper, I'm just going to draw the free body diagram directly on the box. So we have a force of gravity down. We have a normal force normal to the surface, so perpendicular to the surface. And since it's moving to the right, we have a friction force which they define as F to the left. Setting up our, I'm going to do a second free body diagram where I split up this force of gravity into components. And we have normal force, we have force of friction, we have Fg, or let me do mg sine of theta down the ramp, and we have mg cosine of theta into the ramp. So if I want to find the acceleration, it doesn't specify, it does specify positive direction as up the ramp. So setting up a Newton's second law up the ramp, F equals ma, or F net equals mass times acceleration. There is no force up the ramp, so it's just, I don't like how it does that, minus F, because the friction force is pointed the other way, minus mg sine of theta. These two forces right here equals mass times acceleration. And then we can get acceleration by dividing by mass, but we don't need to do that. That's answer choice D right there. Alright, question 2. In figure 1, a cart Y is connected to cart X by a tight string and is also connected to the hanging block mass by a light string that passes over a pulley. Figure 2 shows a system that is identical, but now there's a spring in between the two. We're just describing this picture that's shown. When the systems are released, is the hanging block's acceleration as a function of time the same in both systems, Y or Y not? So I'm going to go with no here. It's not the same. The acceleration versus time graph is not going to be the same. The reason for that is because this spring is not going to provide a consistent, constant force. It's going to like oscillate. It's going to start to like, go bigger and smaller and bigger and smaller. And this one's going to like go down really smooth. This one is going to like speed up and then slow down and then speed up and then slow down, because when that spring like expands and contracts, it's going to not cause a consistent acceleration. So the answer for this one is, I'm going to say, is D. The net force exerted on each system is the same, because if we look at all of these blocks as the system, all of the forces acting from outside the system are the same. So ultimately, all the forces from outside are the same. The problem is that one of these internal to the system, we have a force that's not constant, and that's going to cause the system to have fluctuations in acceleration. Its net acceleration is going to be the same, but not its like acceleration versus time graph. This one's acceleration versus time graph is going to be a nice consistent like line. This one's acceleration versus time graph is going to like fluctuate. They're both going to end up with the same like velocity at the end though, theoretically. Oh, that's question 6. All right, next question. Quick coffee break. All right, a ball of mass m swings in a horizontal circle at the end of a string of radius r at a constant tangential speed of v. A student gradually pulls the string inward, so they're like pulling this ball inward such that the speed is constant. So we're keeping speed constant. Which of the following graphs best represents the acceleration a of the ball as a function of time t? So we're trying to get the acceleration of the ball. This is circular motion, so let's write down our equation for circular motion that we have. Acceleration, centripetal acceleration, is equal to v squared over r. So what's going to happen? We are changing the r. We are keeping v2 constant. One thing I'm kind of liking to do, I'm kind of more starting to do this a little bit more, but I put everything constant on one side of the equation and everything that's changing on the other side. So in this equation, acceleration and radius is changing, v is constant. So let's do this. Acceleration times r equals v squared. This side remains constant. As we pull this ball in, the radius is going to decrease. So we're decreasing the radius, which means as we pull it in, acceleration should increase. So there's only one of these graphs that's showing acceleration increase versus time, and that's B. Only B is showing an increase in acceleration. A is constant, C and D are decreasing, so B has to be the right answer. Now whether it's a linear function or an exponential function, you don't need to know because there's only one that's increasing. We're not given the rate at which he's pulling in this ball, so we don't know that for sure. However, we do know that acceleration has to increase, so the answer is B. 4. A rocket lifts a payload upward from the surface of the Earth. The radius of the Earth is r, the weight of the payload on the surface is w, the force of gravity on the payload, the force of the Earth's gravity on the payload is 1/2 w, when the rocket is what distance away from the Earth. So this is the big G equation. All these radiuses and masses and weights and whatnot. Force of gravity is equal to G m1 m2 over r squared. So once again, this is another equation. This is another question. We're kind of doing what we did in 3, where we're looking how things change in an equation. I'm going to do what I did before. I'm going to put everything that changes on one side and everything that's constant on the other side. The mass of the Earth, the mass of the rocket, and gravitational constant are not changing. What is changing is the weight, which is force of gravity, and the distance away we are from Earth, which is r. So let's put them on the same side. So Fg times r equals a constant. Right? Let's just write constant. The force of Earth's gravity, r squared, not r. The force of Earth's gravity on the payload is 1/2 F. So if we divide that force of gravity by 2, that means r squared needs to be multiplied by 2. And since r is squared, that doesn't mean we want to double r, because double r would mean we quadruple that r squared value. That means we're going to square root of r. So the answer there is B. A student must determine the inertial mass of a block that is pulled across a horizontal surface using a force probe and an accelerometer. The student's data is represented in the graph above. What must the student do to determine the inertial mass of the block? So we're given a graph of force versus acceleration. Whenever we're given, first off, there's a lot of things in this question we haven't talked about before. The phrase inertial just kind of applies to mass within a system. Don't let it confuse you. We have a force probe and an accelerometer, so we can measure. What that means is we're doing an experiment where we can measure force and acceleration, which is what this graph is showing. This graph is showing force and acceleration, and we want to know how we can get mass from this graph. Whenever you're given a graph, the first thing that you should ask yourself is, what are the axes, and then what equation can I use? So we are given force and acceleration. All right, what equation do we know that has both force and acceleration in it? It's the biggest equation in AP physics, F equals ma. We're trying to get mass. Mass would therefore equal force divided by acceleration, which means that we can take the slope of this graph, because the force is the rise, the acceleration is the run. So if we take the rise over run of this data, we can get the mass, which is B. So it's a common type of question, giving you a graph. Just look at what the axes are, and really you should in your mind be thinking, all right, what can the slope of this graph give me, and what can the area under the curve of this graph give me? The slope being what's the rise over run, the area being what is the rise times the run. Great, question 6. The figure above shows a truck pulling 3 crates across a rough road. So we have a rough road, not frictionless, so we are going to have to deal with friction. Which of the following shows the directions of all the horizontal forces acting on the crate? So we don't care about normal and force of gravity. So, or on crate 2. So this crate, I would say, so this crate has that tension from the rope pulling it back. It has a cable, tension from the cable pulling it forward. It has friction pulling it back because it's on a rough road and it's moving this way. Friction opposes motion. And then it also has a normal force from block 3 pulling it back as well. So it's got those. This is the free body diagram. It looks like C is the answer there. All right, moving on. Question 7, a block of mass 2 kilograms slides along a horizontal tabletop. A horizontal applied force of 12 newtons and a vertical applied force of 15 newton act on the block, as shown above. If the coefficient of kinetic friction between the block and the table is 0.2, the friction force exerted on the block is most nearly. Okay, I don't have a calculator. Now I have a calculator. All right, first step, let's look at a free body diagram. I'll do it up here. So we have a force of gravity pointed down, mg pointed down. We have a normal force pointed up, but we also have a 15 newton applied force pointed down as well. This force right here is pushing down into the block, so that's a force acting down. We have a normal force, therefore that's equal and opposite to these two added together. It's not going to be equal to opposite in just force of gravity, because there's an extra force pushing the block into the surface. Normal force is always equal and opposite to the total force into the surface. We have a 12 newton force to the right, and then we also have a force of friction to the left, and this force of friction is what we're solving for. So force of friction is equal to mu times normal force. Normal force is going to be mass times gravity plus the 15 newtons. So that means the friction force is going to be equal to mu, which is 0.2, times mass times gravity, which is 2, times 10 plus 15. So 20 plus 15 times 0.2 is 7 newtons. Force of friction is 7 newtons, which is E. All right, last page. Blocks A and B of masses m and 2m respectively are connected by a light string and pull across a surface of negligible friction with a constant force of F1 as shown above. The acceleration of block is A. The force on the string pulling the block B forward has a magnitude of F2. Which of the following claims correctly describes the relationship between the magnitude of the forces acting on the blocks? So just FYI, whenever I'm reading these paragraphs, for physics, if they usually give you diagrams with these, and the first part of the paragraph is just describing what you're looking at in the diagram. A lot of times I know that, and when you do enough of these problems, when I read the paragraphs, I'm mainly looking for extra added on things that I can't see from the diagram. So for example, what is friction? Is there friction or is there not friction? This diagram doesn't tell me if there's friction or no friction, so I'm looking for that in the paragraph, and it says negligible friction. I'm also looking for what the question is asking in the paragraph, and this question is asking to compare the magnitude of forces between F2 and F1. The rest of the information the picture shows me. So from this picture, I can see that F1 has to be greater than F2. F1 is pulling all of the mass of the system. F2 is only pulling 2m, so 2/3 of the mass. So therefore I know that F1 is bigger than F2. I also know that F2 is going to be 2/3 that of F1, since both accelerate the same. But it doesn't ask me to go that far. It just asks me to say that F1 is greater than F2. Last question, question 9. A launcher with mass M1 is suspended from the ceiling by a string as shown. A block with mass M2 less than M1 is launched horizontally. At the moment of launch, the block has speed of v2 and the launcher has an unknown speed v1 in the opposite direction. Which of the following is true about the forces exerted between the launcher and the block? This one just looks like Newton's third law. If we have the system with a block and a launcher, and we launch the block outward, that means the launcher is also, when that separation happens, they're going to put a force equal and opposite to each other. So the launcher is also going to move backward a little bit when it launches the block forward. So the block and the launcher exert forces of equal magnitudes on each other in opposite directions. So that is answer choice C. Alright, that is it for the FRQ. I'm just double checking to make sure I got them all right. That's good, that's good, that's good. I'm good. Alright, I will see you guys in the FRQ. And, yep, that's it. See you.